Hello, everybody. It is just on the hour for our upcoming webinar, but we'll give a few more minutes for everybody who registered to join in before we start. So stay tuned for another minute or so, and then we'll start. We're very happy to see the registration and the participants growing. We're hitting 80 people already. Okay, I think it's a good time to start. So welcome everybody to this Black Hole PIRE webinar. My name is Dimitrios Psaltis. I'm a professor at the University of Arizona, and I'm the PI of the Black Hole PIRE project. This is the fifth and last session of this semester's series, and the theme of the series for this semester was Astrophysics Empowered by the Event Horizon Telescope. If you have missed the previous webinars or you would like to see them again, I welcome everybody to go on YouTube in the Black Hole PIRE Science channel, where you can see all of them, and you can also see later at the end of the day today's webinar as well. And as we're planning for our next semester, next spring's webinar series, which is going to be on advanced data analysis techniques for the Event Horizon Telescope, I also invite you to join the mailing list and receive registration information and all the material for the upcoming webinars. And Rosie Johnson, our project manager, is posting on the chat various links where you can go and get information about that. Today's webinar, like all of them, will last about an hour, and we're going to have time for everybody's questions. And I will ask everybody to put whatever questions they want, either on the chat or in the Q&A session. And Emanuele, our speaker today, has agreed to give a few breaks in the presentation so that he can take questions. And of course, at the end of the presentation, we can have longer questions for him and conversations with him. What is very important for us and very important for this webinar series is for everybody to fill at the very end a very short 2-minute survey to give us feedback. We have a very capable external evaluation team that actually gets all that feedback information and provides us with ideas and suggestions of how to improve this webinar series. And for those of you that have been part of this series for a few years now, I hope they have seen a lot of improvements, and we really value that feedback. So I will remind everybody at the end, but please make sure you do it. And before I waste any more of Emanuele's time, let me introduce our speaker today. It is my great pleasure to introduce Professor Emanuele Berti from Johns Hopkins University. Emanuele is a theoretical physicist and a world expert in gravitational physics and gravitational wave astronomy. He works on everything that has to do with gravity, black holes, neutron stars, coalescence, stability, evolution, and everything that you can imagine. He has published a large number of very influential papers on testing general relativity and on black hole solutions in modified gravity theories. And he has been very actively involved in the challenge of detecting gravitational waves from space with LISA. Today, he's going to talk to us about the Kerr space-time and beyond, or black holes in the Kerr space-times and beyond. And before, as I said, I waste any more time, Emanuele, you have the floor. Thank you very much for joining us.
Thank you so much, Dimitris, for the nice introduction. I'll try to share my screen.
Please do.
Hopefully everything works. You see it?
No, we see your emails.
What about now?
Now we see it, yes.
Okay, So, can I start?
Go ahead.
So, thanks so much to Dimitris and the rest of the Black Hole PIRE group for inviting me to give this talk. I will be talking about Kerr black holes and black hole solutions beyond general relativity and how we can test whether general relativity is the correct theory of gravity by looking at black holes. I will start by giving a little overview of the history of this whole research field, how we started understanding that there are black hole solutions in general relativity in the first place, how they became an important part of how we do physics and astronomy today. And then in the second part of my talk, I will discuss what we know about black hole solutions beyond general relativity. Then I will discuss what we can learn about these beyond GR black hole solutions, if they exist, using the Event Horizon Telescope and gravitational wave observations. And finally, I will try to take a more general approach, and instead of considering black hole solutions on a theory by theory basis, I will talk about the possibility of parametrizing deviations from general relativity, and I'll discuss what we can learn from these parametrizations. I had to say that most of the work that I will discuss is really done to the hard work of many students and postdocs here at Johns Hopkins. The ones that you see at the top are my current postdocs and students, and the ones at the bottom are former postdocs and students that took part in the work I will describe today. So let me start by discussing black hole solutions in general relativity. This is probably a story that most of you know, but I think it's instructive to think about it for a few minutes just to realize how far we have come. Of course, everything starts in November 1915 when Einstein presents the equations of general relativity to the Prussian Academy of Science. And the equations were so complicated that no one thought that it would be even possible to find analytical solutions. But Schwarzschild, soon after, discovered the famous Schwarzschild solution that now we know describes a non-rotating black hole. And it's interesting, of course, that this solution was considered a mathematical curiosity in the beginning. It was called the Schwarzschild singularity because it was thought they had a singularity at the event horizon. Now we know the only real singularity is at the center, but it was not accepted as a physically relevant solution for a very long time. Things started changing in the 30s when Chandra, who at the time was a student, won a scholarship to study in Cambridge. And on the long boat trip from India to the UK, he famously combined the laws of quantum mechanics that at the time were pretty new, in particular the Fermi exclusion principle was, the Pauli exclusion principle was a very new thing. And he combined these ideas with special relativity to understand that stars, white dwarfs, cannot survive gravitational collapse. And it's known, of course, that when he went to the UK, Sir Arthur Eddington, who was the most famous astrophysicist of his time, rejected this conclusion and publicly called it a stellar buffoonery. So Chandra left the UK, moved to Chicago, and his work was vindicated only many years later in 1983 with the Nobel Prize. Black hole solutions became something that was a physical possibility in 1939 when Oppenheimer and Snyder understood that continued gravitational collapse could lead to the formation of a black hole. But that study was pretty much itself a singularity in the sense that it lay dormant for many, many years, mainly because Oppenheimer, of course, had to start working on the Manhattan Project, and he was distracted by World War II and other famous events in the history of physics. John Wheeler was also part of the story. He was, of course, a nuclear physicist. He participated in the Manhattan Project himself. And after the war ended, Wheeler decided to use his expertise in nuclear physics to understand whether gravitational collapse was possible in general. And so he formed a group of students, including Kip Thorne and many others, and he returned to this problem of continued gravitational collapse. Another turning point in this story happens in 1963, when there are two crucial developments. One is mathematical. Kerr discovered famously the solution that describes rotating black holes. This was crucial because every star in the universe rotates, and by conservation of angular momentum, we expect the gravitational collapse should lead, if anything, to a rotating black hole solution. Of course, the importance of this mathematical discovery was not appreciated by astronomers, but it's curious that in 1963, there was another major advance. What we now understand was the discovery of the first supermassive black hole, what was at the time called a quasar, by Martin Schmidt at Caltech. So both observationally and theoretically in 1963 is a key year. In the late 1960s and in the 1970s, of course, Kip Thorne's group led a lot of progress in the development of the theory of black holes. And in particular, one of Kip's students, Sol Tiukolsky, laid the foundations to understand black hole stability and dynamics by writing down the equation that describes perturbations of rotating black holes. Finally, another key result in this story, of course, was the discovery by Roger Penrose that gravitational collapse inevitably leads to singularities. This relies on very general theorems that do not even assume the equations of general relativity. And all of this work, of course, was rewarded with the latest Nobel Prize. I have to say that there's a second golden age going on now. And this second golden age was spearheaded mainly by two events. The first is famously the discovery of gravitational waves in 2015 with GW150914. And the second event, obviously, which was acknowledged with the latest Nobel Prize, is the understanding that there are massive black holes both at the center of our own galaxy and at the center of other galaxies. You see here the famous image of the black hole at the center of M87. And we now understand, as Chandra famously put it, that these exact solutions of the Einstein equations of general relativity provide the absolutely exact representation of untold numbers of massive black holes that populate the universe. It's also interesting to see the relative role of astrophysics and of black hole physics in the whole body of physics as a discipline. What you see here is an interesting plot of the fields that were awarded the Nobel Prize as a function of time. And you can see that astrophysics, astronomy, and cosmology are playing a dominant role in the last few years. And I highlighted in yellow here several Nobel Prizes that were awarded after Chandrasekhar that are related to black holes in some way or another. Now, the key question that we'll address in this talk is, are we really sure that these astronomical objects are indeed the Kerr solutions of general relativity? How can we be sure? So first of all, if I want to ask a question like that, I'd better come up with a justification for why we think there could be black hole solutions that are not the ones of general relativity. So we'll start discussing theories beyond general relativity that have been proposed, their motivation, and what we know about black hole solutions in these theories. I'll start with this relatively complicated diagram that comes from a review that we wrote back in 2015. The key idea of this complicated diagram is that you can think of the Einstein equations as a consequence of a general theorem that is called Lovelock's theorem that you see stated up here. The idea is that if your space-time is four-dimensional, if the weak equivalence principle holds so that you construct a tensor that has to be divergence-free, which implies also the conservation of the stress energy tensor, if you want to construct your field equations only from the metric, and if you want to have diff invariance, then inevitably your field equations reduce to the Einstein equations plus possibly a cosmological constant. So there are four key assumptions that I highlighted in red. You can violate them. You can decide that you're willing to live without one of these assumptions. And pretty much in every single case, violating one of these assumptions means that you have to introduce additional degrees of freedom. For example, if you introduce diff invariance, you will have theories like massive gravity or Lorentz violating theories. And if you add extra fields, in general, these extra fields can be non-dynamical or dynamical. One of the most popular theories that people have considered historically is scalar tensor gravity, which comes in many different flavors. It was introduced initially with completely different motivations, but it has been studied in a lot of depth. And whenever you look at one of these modified theories of gravity, you want to have some minimal requirements. First of all, there should be actual physical theories for which you can write down an action principle. They should be well posed. That means that if you assign initial data on some hypersurface, the equations tell you how to evolve those initial data into the future. They should be testable, because you can come up with a theory that is, for all practical purposes, indistinguishable from GR, and then we really don't know what to do with it. And then they should predict all of these spectacular observations that have led to the Nobel Prizes that I was discussing before, in particular the existence of black holes, of neutron stars, and the theory should be compatible with the cosmological observations that we have. These are very tall requirements. So one thing that happens in general when you consider these modified theories of gravity is that, unfortunately, very often they lead to black hole solutions that are exactly the same as in GR. Take, for example, what is called as Bergman-Wagoner theory sometimes. This is one of the simplest variants of scalar tensor gravity. If you look at the evolution of compact binaries in a theory like Bergman-Wagoner theory, what you find out is that there is in general dipole emission. There is quadrupolar emission. This is the orbital period derivative. There are also additional complications that can appear in these terms when your scalar is massive, but I will not go into that. The key point is that the dipolar emission depends on certain quantities that are called sensitivities. Now, for black holes, these sensitivities are equal to 1/2. And so if you take a black hole binary, the black hole binary evolution in scalar tensor gravity is going to be identical to the evolution in general relativity. Not only that, black hole solutions in scalar tensor gravity were proven back in the 60s to be identical to the solutions of general relativity, in the sense that you find a Schwarzschild metric with a constant trivial scalar field. This was proven by Hawking, Thorne, and Dikla, and many other people. So you are led to the conclusion that if you take at least the simple variants of scalar tensor gravity, both the solutions and their dynamics are the same as in general relativity. So there is no way that you can test whether you have a black hole binary in GR or in scalar tensor gravity. There are ways around this. One way is to introduce matter, but then you wouldn't be looking at black holes, and that's not the topic of this talk. A second way is to modify the boundary conditions. So you can introduce cosmological boundary conditions. This leads to hair growth, but the hair growth produced by cosmological boundary conditions is so small that it's unobservable. And there's a third way out that we'll discuss later. That's the case in which curvature itself sources the scalar field in certain special classes of beyond GR theories. So how can we look at this gigantic zoo of beyond GR theories? One way is to adopt what is called an effective field theory approach. The idea is that you take the gravitational action and you expand all operators in the action in terms of some length scale. This length scale has to be macroscopic if you want it to be relevant to astrophysical black hole tests, because the typical scale involved in black hole observations is of order maybe 1 kilometer for a black hole of a solar mass. So what you do is you write down your theory as the Einstein-Hilbert action here, plus a series of corrections that are suppressed by some powers of length. And if you do this systematically, you get a bunch of corrections. They go under various names. One correction is the so-called Einstein scalar or Einstein dilaton Gauss-Bonnet term, which is here expanded to linear order in the scalar field. You get parity violating terms that go under the name of dynamical Chern-Simons theory. And then you can get cubic corrections that include things like Einsteinian cubic gravity, parity breaking violation of that theory, and so on. You can also go to next order. And if you do not include additional scalar degrees of freedom, you find theories that were studied by people like Henlich, Gorbenko, Huang, and Senatore. These are suppressed by very high powers of the curvature. Now, I will focus mostly on this theory, and I have a few valid reasons for this. One is that this particular theory is different from all of the others that come from varying this action in the sense that it leads to second order equations of motion. That's important because it means that, at least in principle, the theory is not pathological. It doesn't contain what are called ghosts or the Ostrogradsky instability. There's a second reason why this theory is interesting from the point of view of the talk that I'm giving today. And that's the fact that this particular theory represents a loophole in the no-hair theorems of beyond GR theories, in the following sense. You can write down the most general Lagrangian that gives you an Einstein scalar tensor theory that is of second order in the equations of motion. This is called the Hordensky Lagrangian. It's a complicated monster that I write down here. You don't need to look at these equations for more than 5 seconds. What matters here is that for a certain special choice of the functions that appear in this Lagrangian, you recover Einstein's scalar Gauss-Bonnet gravity with a generic coupling function f of phi. In the case where your theory is invariant under a shift of the scalar field, you say that the theory is shift invariant, obviously. And this is a special case also because adding a constant to the scalar field, this corresponds to the case I was showing before. If you add a constant to the scalar field, this constant does not affect the equations of motion because the Gauss-Bonnet term G, which is the same thing that I called RGB here, is a topological invariant. It's only a boundary term when you vary the action. So it doesn't affect the equations of motion. Anyway, the key point of these two slides is that Einstein's scalar Gauss-Bonnet gravity is a special case of both general scalar tensor theories that give you reasonable field equations, and you can think of it as some low energy limit of string theory in the sense that you get it in an effective field theory expansion when you take proposed generalizations of general relativity that are quantizable and you take their low energy limit. So let me explain why these theories are relevant to the study of black hole solutions beyond GR. There is something called spontaneous scalarization that has been studied for a long time in the context of neutron stars in standard scalar tensor theories of gravity. The idea here is that if you take a standard scalar tensor theory of gravity with a non-zero matter action, and you write down the equations of motion, you get some modifications of the Einstein equations and a Klein-Gordon-like equation for your scalar field, which is sourced by the trace of the stress energy tensor. Now, focus on this second equation down here. Ignore the presence of a potential because we're not interested in cosmological corrections. And try to understand what happens when you take spherically symmetric solutions in this particular theory. Well, you can do this as a back of the envelope calculation. Assume that your solutions are not time dependent so that your D'Alembertian operator becomes a Poisson operator. Take also the Newtonian limit to make things simple. Then you're going to have some coupling between matter and your scalar field, which is described by this function alpha, which depends on some constant beta. You can approximate the trace of the stress energy tensor by basically the energy density. If you have a star, the energy density is m over r cubed. So you can write down your Poisson equation with a source term on the right-hand side. And what you realize is that basically this solution is a Klein-Gordon equation with a mass term. The mass term depends on the sign of this constant beta and on k squared, which is a constant related to the compactness of the star. You see here. So you can solve this equation analytically by using spherical Bessel function, which is just a fancy word for a cinch in this case. And what you find is that your scalar field inside the star will diverge when the compactness of the star and the beta parameter are related in a certain way. So if beta is a certain special sign and your star is sufficiently compact, the scalar field can grow. This is a phase transition that is called spontaneous scalarization. And it basically happens when you look at the reason why this is so. It happens because you have a tachyonic mass term in your scalar field equation. So whenever there is a change of sign in beta and the term on the right-hand side is large enough, the scalar field will grow. Now, a very similar thing happens in Einstein's scalar Gauss-Bonnet gravity. What you can do is you can prove it analytically. You write down the equations of motion for the scalar field, you integrate them, you find, you multiply by the FD phi, you integrate, you find an object on the right-hand side that you can prove vanishes identically. And so your black hole solutions are going to be the black hole solutions of GR only when the second derivative of the coupling function has a certain sign. Otherwise, you are free to have solutions which have a non-trivial scalar field profile. And you can also see this by linearizing the field equations. Just like in the case of stars, you get a tachyonic term, which can become large enough in some cases, and so produce a growth of the scalar field. The main difference here is that you don't need matter. What causes the growth of the scalar field is the Gauss-Bonnet invariant, which is the curvature of your background spacetime. So if you start from a black hole solution in general relativity, the Gauss-Bonnet invariant is going to be non-zero. Remember from your standard GR classes that the Ricci tensor and the Ricci scalar are both equal to 0, but Riemann is not. It's m over r cubed. So if you have a black hole background, this object here can be non-zero. When the sign of this term is negative, you can have a growth, a tachyonic growth of your scalar field. So this has been studied for several models. The minimal model that you can take is quadratic. You can also consider exponential models. And people have studied the stability of the solutions. I will not say much about this. I will just say that the minimal scalarization model in general leads to solutions that are unstable, but you can cure their stability by going to nonlinear models. People have also studied spinning black hole solutions in these theories, and they found that the domain in which you can find scalarized solutions shrinks as you increase the spin of the solutions. But a recent development is that you don't even need to have a negative sign in the coupling function. And the reason is that you can take a second look at this equation. And if you take a Kerr black hole background now, what you realize is that the Gauss-Bonnet invariant for the Kerr solution can become negative close to the horizon as long as the spin of the Kerr black hole solution is large enough, larger than about 0.5. So you can have the ordinary sign for your coupling function, and now it's your Gauss-Bonnet invariant that will become negative close to the horizon when the solution is spinning fast enough. There's a couple of groups. Well, first of all, Dim and others realized that this would be the case. And then Carlos Cerdeiro and us, we put some papers in PRL recently where we show that you can start from solutions of GR. And if the solutions spin fast enough, they can scalarize, which is interesting for LIGO because the black holes that we see in LIGO have a spin that is larger than 0.5. So, of course, the hard part, once you have these theories, is to compute the dynamics of binaries. And this is a very complicated problem. I will not go into too much of the technical details, but there was progress that was made both on the analytical side through the work of several people and on the numerical side, so that now we have at least the equations of motion in these theories, they are surprisingly well behaved. And some people, including people that are in the audience today, worked on the numerical evolution, and they found waveforms in these modified theories of gravity that we can, at least in principle, compare with the observations by LIGO. To summarize this first part of the talk, there is a special class of theories of gravity called Einstein scalar Gauss-Bonnet, which evades the no-hair theorems. In these theories, you can have scalarized black hole solutions. At least in some of these theories, they are radially stable and they are thermodynamically stable compared to the solutions of GR. These solutions are interesting phenomenologically because you can compare them against observations of black hole shadows or against LIGO observations. There is a lot of work to be done in terms of understanding the dynamics of these theories, but several groups are pushing hard in that direction. So this is my first break. I can take one or two questions and then move on.
Thank you, Emanuele. Any questions in the chat or the Q&A? I have a really quick one, and maybe that will start the conversation. You can move on. As you said, there is different coupling functions between the various fields and the Einstein-Hilbert field, or the metric, that different groups have calculated different black hole solutions for. What are all these different functions give the same scale of at which you expect to see deviations from Kerr? Like, is in some of them the smaller black holes the ones that deviate, some of them the large black holes, or how does that depend on the fact that we have the supermassive and the stellar mass black holes and that?
Yeah, so the key answer here is that the coupling between the scalar and the higher order curvature terms scales with the curvature scale of your background solution. So in a sense, it's easier to constrain these coupling constants by looking at small black holes, because small black holes have a larger curvature scale. So in general, you would expect that you will get the better constraints on these solutions from astrophysical, say, stellar origin black holes than from supermassive black holes.
Thank you. And we have one question. Somebody says he's an undergraduate and haven't seen the solutions before. So if you can, at the end of the presentation, put a link to where he can see those solutions, that would be wonderful.
Let me say that all of these little numbers that you see here are archive numbers. So when you look at the presentation again, all the links here are the papers in which these solutions were found.
And one last question, is there a fundamental difference when talking about scalarized solutions versus hairy solutions?
Yes, very good question. So I have to say that hairy black hole solutions in Einstein-Dilaton Gauss-Bonnet theories were known for a long time. In fact, the first paper to compute black hole solutions in these theories was by Panagiota Kandi back in 1994 or so. There they considered the theory which has an exponential coupling function. And let me see if I wrote it down here. It's this theory over here. This is the one that you get from the low energy limit of string theory. What happens is that this is a theory in which the second derivative of f with respect to the scalar field vanishes identically. So these are theories in which you find black hole solutions that are always different from the black hole solutions of general relativity and do not reduce to the black hole solutions of general relativity. The reason why people got very interested in this spontaneous scalarization phenomenon is that you have a continuous limit in which your non-GR solutions reduce to the solutions of GR. Okay, so that's the main difference between this spontaneous scalarization that people have been studying recently and hairy black hole solutions that were known even before.
Thank you, Emanuele. There's more questions coming in, but let's move on. It's 34 minutes after the hour, and then we can continue afterwards.
Yeah, okay. So let me go quickly because I know I'm going to run out of time. So in this part of the talk, I will try to introduce what we can learn about beyond GR black holes from the Event Horizon Telescope and gravitational waves. Most of the reasoning on testing theories beyond general relativity goes back to the so-called Will-Nordtvedt parametrized post-Newtonian formalism. The idea here is that we know, as I said earlier, that if you want to go beyond general relativity, you need to violate some of the underlying hypotheses that lead you to the Einstein equations. The key assumption behind the Einstein equations is what is called Einstein's equivalence principle. It's the combination of the weak equivalence principle, basically the idea that all objects fall in the same way independently of their internal structure and composition, local Lorentz invariance and local position invariance, the fact that non-gravitational experiments will yield the same result no matter where in the universe and you do them and how fast their local inertial frame is moving. So all of this leads to the conclusion that gravity must be a metric theory. It doesn't tell you what the field equations have to be, but it tells you that gravity has to be space-time curvature. Now, the different theories of gravity that people had already studied back in the 60s differ in their prediction for the amount of space-time curvature in the field equations. So what Cliff, Will, and Nordtvedt did back in the 60s was they parametrized the metric components, say, in the solar system around the sun, in terms of certain parameters that will have to be either 1 or 0 in general relativity, and they can be different in modified theories of gravity. One of the most famous parameters in this case is the so-called parameter gamma that measures the amount of space-time curvature in the solar system. This parameter gamma has been tested over time better and better, and now the most stringent bound comes from the Cassini mission. We know that this parameter gamma has to be unity within 1 part in 10 to the 5. However, all of the corrections that we can test in the solar system are small, and the reason is easy to understand. If you take the strength of gravity around the sun, that's measured by the parameter m over r, and for the sun, the parameter m over r is of order about 1 part in a million. So if you want to test higher order corrections to the metric, you'd better be in an environment where gravity is very strong. Now, Dimitris and others recently showed that you can set constraints on higher order parametrized post-Newtonian corrections by looking at observations of the light ring in the Event Horizon Telescope measurements of M87. And in particular, they mapped these second order PPN corrections to certain model metrics that were introduced by Dimitris and Johannes and Johansen earlier on. And they showed that you can get interesting bounds on these two PPN parameters. I had to say that you got to be careful in interpreting these bounds. In particular, people have pointed out that accretion physics is not well understood around black holes. And other people have pointed out that the interpretation of these bounds depends on what you choose for your priors. But from the point of view of the discussion today, the most interesting thing that makes these bounds different from the bounds that you can get from gravitational waves is that these are bounds on the spacetime metric. So if you get modified theories of gravity in which your black hole solutions are exactly the same as in GR, looking at these bounds doesn't tell you much of anything about the theories because the metric is going to be the same in both general relativity and these modified theories of gravity. Take, for example, the scalar tensor theories I was talking about before. What is different in gravitational waves is that gravitational waves look at the dynamics of black holes. So what you get in a gravitational wave signal can differ even if the background metric is the same. However, there is a deep relation between the measurements of the light ring, the ones that are being done by the Event Horizon Telescope, and the quasi-normal mode measurements. And this link was understood a very long time ago by Gebel. As I will explain in a minute, you can think of oscillations of black holes and the gravitational waves that they produce as being predominantly described by perturbations of light rays moving at the light ring, okay? So the frequencies of oscillation of a black hole and their damping time are intrinsically related to the perturbations of a black hole at the location of the light ring and the time scale over which these perturbations grow. The way to understand this is to work out the equations that describe perturbations of a black hole induced by different fields. The simplest case that I can think of is the case of of some scalar field that is small, so that it doesn't produce perturbations in the curvature. If you write down the Klein-Gordon equation in the background of a black hole, you find that it's described by a Schrödinger-like equation. You separate the time dependence by using a Fourier analysis. You separate the angular dependence by using spherical harmonics. You find a radial equation that is basically of the Schrödinger form. This omega plays the role of the energy, and there is a potential, a radial potential that is the equivalent of, say, the potential that appears in the hydrogen atom in quantum mechanics. Now, because you have a scattering equation, you can study the problem by using tools from quantum mechanics. In particular, you can impose that you have only ingoing waves at the black hole horizon, because that's the characterizing feature of the horizon of a black hole, and you only have outgoing waves at infinity. Once you impose these conditions, you get an eigenvalue equation. The main difference with respect to quantum mechanics is that now your system is dissipative. It doesn't conserve energy. So you don't have all the beautiful properties of hermiticity, self-adjointness that you have in quantum mechanics. And these frequencies, omega, turn out to be complex. The real part is the actual oscillation frequency. The imaginary part is the inverse of the damping time. Why do you have a damping time? Because you are emitting gravitational waves and you have a sink of energy both at the horizon and at infinity. Now, you can analyze the wave equation using WKB methods from non-relativistic quantum mechanics, and you find that the real part of the frequency is associated with the second derivative of the potential at the peak, and the imaginary part is similarly associated with features of the potential at the peak. And the interesting thing, which is not a coincidence, is that this peak is located almost exactly, and in some cases exactly, at the location of the light ring. So perturbations of a black hole and their frequencies are described by perturbations of light ring orbits. Now, you can compute the spectra using techniques that I will not describe, and what you find is that each spherical harmonic index, L equal 2, L equal 3, and so on, has a spectrum that is discrete. The dominant frequency in gravitational radiation is going to be the one that has the smallest imaginary part, because it's the one that has the longest damping time, so it's going to survive the longest. And the interesting thing is that when you introduce rotation, each of these modes, for example, this one here, is going to break into a series of modes that depend on the azimuthal index of the angular perturbations. So if you have a rotating black hole and you measure both the real and the imaginary part of the frequency, you can determine what the mass and the spin of that black hole are. And because in general relativity, all black hole solutions depend only on the mass and spin, we are ignoring the electric charge. Once you have measured one of these points, say this point over here, the background solution is fixed. If you measure any other mode, you have a test of general relativity. Or more precisely, you have a test that the object you are looking at is a Kerr black hole solution in general relativity. This is called black hole spectroscopy because basically what you're doing is the same thing that people were doing in the early days of quantum mechanics. You are measuring spectral lines, and if you're looking at a hydrogen atom, all of those spectral lines have to fall onto, I don't know, the Balmer series. This is exactly the same thing that is happening here. Now, we can do this using both Earth-based detectors like LIGO and space-based detectors like LISA. The main thing that changes is the mass scale. The mass scale determines the frequency of the oscillations. So if you take two black holes that merge and form a final black hole about 100 solar masses, the frequency of oscillation of the final black hole is going to be of order about 200 hertz. But if you rescale this to, say, a black hole of mass 10 to the 6, then the typical frequency is going to be of order 10 to the minus 2 hertz. And then black holes like the one at the center of our own galaxy, which have a mass of 10 to the 6, are going to be ideal targets for a mission like LISA. What is interesting is that if you want to measure more than one mode, then you need very high sensitivity for the detectors on Earth. This is a calculation that we did some years ago, where we took astrophysical models and we asked how many events, for how many events can I measure the ring down, and for how many events can I also detect an additional mode and therefore perform the spectroscopic tests that I'm talking about. Now, these models you don't need to care about, but they are different astrophysical models. What you see is that a detection was pretty easy to do even in the first observing run of LIGO. But if you want to perform these tests, you need more advanced ground-based detectors. While with a detector like LISA, every time you observe a merger of a black hole binary, the signal-to-noise ratio is going to be large enough that you can always do these spectroscopy tests. Not only that, but you can do them at larger redshift because LISA is sensitive to binaries that will merge basically throughout the whole universe. So what you see here is a plot of the redshift out to which you can perform the spectroscopy tests with different classes of detectors, LIGO 1 or 2, advanced LIGO, various upgrades of LIGO up to Voyager, Einstein Telescope, Cosmic Explorer, and so on. And you see that all of these Earth-based detectors will give you tests of Kerr black holes out to redshifts of a few, or in the best case, maybe 10, while LISA, if black holes merge in the universe, will test Kerr black hole solutions throughout the universe. Now, how do we know how many modes we can detect? Well, to do that, you need to use numerical relativity simulations. I don't think this is particularly interesting, and I'm slowly running out of time, so I'm going to skip this part of the discussion. Let me only tell you that because there are different overtones for any index L, you can look at the overtones and do spectroscopic tests using the overtones. And this is something that has already been exploited by Max Easy and others. What they did was they showed that if you include more than one overtone in the dominant mode of the radiation for the very first gravitational wave observation, then you can infer a value of the mass and the spin that is better determined than you would if you only included the fundamental mode. This was understood in black hole perturbation theory for a long time, since the 1980s, when Lieber pointed this out in the context of particles falling into black holes. Possibly the most interesting thing that they did in this paper is that they tried to do black hole spectroscopy and by measuring the frequency of the first overtone. And as you can see, the measurement is not that good. What they claim is that they have an accuracy of about 20% in the measurement of the first overtone's frequency. And so they say this is the first no-hair test that has been performed, which is true to some level of accuracy. But you know, if you really want to test black hole spectroscopy, you need more sensitive detectors. So this is the bottom line of my second part of the discussion. Black hole spectroscopy gives null tests within general relativity, in the sense that if you measure that these frequencies are consistent with the predictions of general relativity, you can conclude that the black hole you are observing in gravitational waves is consistent with Kerr to a certain level of accuracy, epsilon. Now, the key question that we'll address in the last part of the talk is, can we go beyond null tests? And in particular, if we see deviations in any of these frequencies, are they going to tell us something about possible corrections to general relativity and the underlying theory of gravity? I'm going to pause for a second and then I'll move on if there are no questions.
I think we have a couple of questions from mostly from the previous third of the talk. So I would say, since we're running late, why don't you spend maybe 5-6 minutes for the last part, and then we'll have some conversation at the end. Thank you.
Sounds good. Okay. So let me explain what I mean when I say that I want to introduce parametrizations. Suppose that you take two black holes that go around each other and you look at the gravitational wave signal that they emit in the frequency domain. Now, this gravitational wave signal will be given by a certain amplitude, A in GR, multiplied by a certain phase, psi in GR. In principle, if you are very good at doing post-Newtonian calculations, you can determine this amplitude and this phase to infinite accuracy. In practice, maybe not, but okay. That's a different question that has to do with our ability to compute things within general relativity. Now, the idea is, if I look at the expansion of the phase, which is the quantity that gravitational wave detectors measure most accurately, this expansion can be written down as a power series in the frequency or in the orbital velocity of the binary, which is the same. Each of these coefficients that appear in the phasing is determined uniquely in general relativity. For example, if you have a binary of black holes that are non-spinning, all of these coefficients will depend on the masses of the binary components. So what you can do is say, what if my theory of gravity is not general relativity? In general, I expect to have corrections to both the amplitude and the phase. And in each specific theory of gravity, I should be able to compute these corrections. So what LIGO has been doing is they have been saying, let's assume that the values of these coefficients are the ones given in general relativity. If we measure the deviation delta P from these general relativity parameters, whenever I see that that measurement is consistent with 0, I have an additional test of general relativity. Of course, different theories of gravity will predict non-zero coefficients at different post-Newtonian orders. So if you measure that one of these coefficients is non-zero, then you can say, maybe my theory of gravity was not GR, but, for example, a scalar tensor theory that will predict dipolar radiation, okay? So the idea is that by mapping these coefficients to specific theories, you can then reconstruct the theory that gave you a non-general relativity in spiral of your compact binary. Now, this is well and good, but when you think about it, it's very hard to do in the merger phase because it relies on the fact that we know the post-Newtonian expansion very accurately. So we cannot do a parametrized expansion in the strong field region of the merger because we don't know the background solution analytically. If you want to do a parametrized expansion of the kind that Will and Nordtvedt were doing, you should know your background solution. Now, fortunately, this is exactly what we do when we look at black hole perturbations in the way that I was explaining before. You can take your background wave equation, which is a Schrödinger equation, written here in a slightly different form, and you can say, if I have deviations from general relativity, they will appear as small corrections to the potentials that appear in the wave equation. If you give me any theory, I'll be able to map it to the corrections to these potentials. So let's take for simplicity a non-rotating black hole. I will explain later on the complications that appear when your black hole is rotating. If you take a non-rotating black hole in general relativity, the perturbation equations split in two sets depending on the parity of the perturbations, whether they are odd or even under parity. So the potentials for the odd and even perturbations were computed a long time ago by Repee Wheeler and Zerilli, and their quasi-normal mode spectrum was computed by Chandrasekhar and Dekdala in 1975, and they showed that the even and odd perturbations have exactly the same spectrum. Remember those dots that I was drawing before? They're exactly the same. This is not a miracle, but I don't have time to enter into the reason why this happens. Now, suppose that you give me a theory that is not general relativity. In general, what it will do is it will modify the potentials for both even and odd perturbations. Not only that, because as I explained earlier, any modified theory of gravity introduces additional degrees of freedom, I expect that in general, perturbations due to a scalar field on top of my background will also be modified. So the Klein-Gordon equation will obtain corrections that depend on the coupling parameter between, say, my scalar field and the metric. All of the quasi-normal mode spectra will correspondingly be modified. The interesting thing is that you can compute these modifications once and for all for any arbitrary expansion, leaving these coefficients alpha and beta completely generic. So you are parametrizing the whole spectrum. Then if you give me a theory, your specific theory will determine the values of these coefficients alpha and beta. Once I have computed these numbers here, E and D, which are arbitrary expansion coefficients in this power series, you specify the theory and I can tell you what the frequencies are going to be. So this is a program that we carried on. We have computed all of these coefficients. You don't want to know the details. There's some convergence properties that we have determined analytically. They confirm our numerics. What we find is that in general, you're going to break the isospectrality between the even and odd modes, because that's a very special property of general relativity. And more interestingly, remember all of those theories I was describing before? You can map them onto this perturbative formalism. So say that you take effective field theory corrections that are quartic in the curvature of the kind that I was writing down much earlier. These are the Endlich, Senatore, Gorbenko modifications I was talking about. Those give you a very specific prediction for the modification of the gravitational potential. They had been computed before in this specific theory of gravity. We computed them again using our generic formalism, and we find that the results agree. Or you can think of even more simple things as being perturbations on top of GR. Say you take electromagnetic fields. You know that if you add electromagnetic fields to general relativity, you get something called the Reissner Nordstrom solution. We generally ignore this because we know that in astrophysics, the charge has to be small. Okay, but you can say, I can take my Reissner Nordstrom perturbation equations, I treat the charge as a small parameter. I can map all of these onto the formalism that I just described, and I get that the results are in very good agreement, at least as long as the charge is small, which is the limit of this perturbative formalism. And you can repeat the exercise. Rotation can be treated as a small perturbation on top of the Schwarzschild solution, same story. But when you introduce modified theories of gravity in general, the complication is that the scalar, electromagnetic, and gravitational degrees of freedom will couple with each other. So this is a much more complicated problem. We have already solved it. You don't need to worry about it. What we found is that in general, you can determine the way these different potentials couple to each other. You can compute the perturbations generically, and then you can map them to specific theories. So there's a difference between degenerate and non-degenerate perturbation theory. It is too technical, but you can do this and you can map the results onto all of the theories I was discussing before. Dynamical Chern-Simons, it works. Ordesky theories of gravity, it works. Effective field theory modifications, it works, okay? So the bottom line of this very technical part of my talk was, for dynamical perturbations on non-rotating black holes, we know exactly what to do. If these corrections are small, you can, in principle, give me any field equations, write them down, and I know how the quasi-normal mode frequencies are going to differ from the quasi-normal mode frequencies in GR. This means that if I measure a non-zero deviation, in principle, I can map it to one of the million specific gravitational theories that are not GR that you can give me. The complication appears when you look at rotating solutions. And There are many reasons why this is more complicated. We can discuss it maybe later because I'm running out of time. But the equations become non-separable. So you need to introduce additional tricks to separate the wave equations. This has not been done in full generality for gravitational perturbations. It has only been done for scalar perturbations in specific effective field theory modifications of general relativity. What we have done is a simple uh, uh, data analysis exercise. We asked, suppose that the modifications to your frequencies and damping times appear as a power series correction in the coupling constant of the theory and in the spin. Then you can ask, I'm going to have a bunch of different parameters now. One will describe the corrections with respect to general relativity. The other will describe the corrections that appear because my solution is rotating. But if I have a single theory that is the true theory of gravity, then all of these gammas are going to be the same. So the idea of this paper we wrote with Andrea Maselli was, suppose that we observe n gravitational wave events. Because all of these corrections are going to be the same, I can try and understand how many events I will need to determine uniquely all of the correction coefficients that appear due to the small rotation expansion and to the expansion around the solutions of general relativity. It turns out, long story short, that just a handful of observations can in principle constrain several of these deviations, and therefore it can determine what underlying theory of gravity was modifying your quasi-normal mode frequencies, even for rotating black holes. That's my last slide. This is a very short summary of everything I said. And Dimitris and all of the other black hole PIRE people told me several times that I should remind you all to fill the questionnaire. I hope the talk was not too technical, and I hope that each and every one of you got something out of it.
Thank you very much, Emanuele, and thank you everybody for staying throughout this talk. It was a really wonderful summary of work that was done for testing the Kerr spacetime, especially with gravitational wave observations. I wanted to point out that there is on the chat a direct link to the questionnaire, and we would all really appreciate it if you could fill it, because, as I said in the beginning, the feedback is very important for us. There is, we're at the hour time, but I think whoever wants to stay, there's some time that we can spend, maybe 10 more minutes to answer some of the questions. And thanks again, and I say a lot of thanks and clapping in the chat for Emanuele. To go back to the questions, we have some from the very first part of your presentation. And one was, are the violations that you described before, all these extra degrees of freedom, real violations of the no-hair conjecture? In other words, are the solutions characterized by global charges or not?
Yes. Yes. So this probably comes from someone with a mathematical mindset. I don't know who asked the question, but there are two different ways of characterizing solutions that differ from general relativity. Those that have a primary charge or a secondary charge. Now, in these solutions, you can indeed define a scalar charge that is non-zero, and you can measure it. Whether that charge is a conserved charge or not depends on the particular theory that you're considering. But in general, yes, one of the interesting features of these scalarized black hole solutions is that they will give you non-zero charges. Another name for those charges are the sensitivities that I was describing before. The reason why the spiral, for example, in Einstein scalar Gauss-Bonnet gravity differs from the spiral in ordinary general relativity is that you have these non-zero charges, and therefore you have the production of dipolar radiation in a black hole binary, which, if you remember, is something that is not possible in ordinary scalar tensor gravity. The first paper that studied the dipolar radiation in these theories within an EFT framework and in post-Newtonian gravity was a paper by Leo Stein and Ken Tyagi and Nico Younes. I know that at least Leo was in the audience today. But yeah, what we are trying to do now is go beyond the perturbative approximation and compute more accurately the in spiral of these binaries and also their merger. There has been spectacular progress recently, in particular by Justin Ripley, Franz Pretorius, Will List, and others who have been trying to evolve the equations of Einstein's scalar Gauss bonding gravity numerically, even beyond the approximation.
And Leo just posted on the chat the link to the paper that you just described that he was on.
Great.
Very good. We have a much, and the Ripley paper, thank you, Leo. And we have a much broader question for you, so we could have an entire conference on it, but I'm just going to pose it to you to ask for a very concise answer. What is the motivation to develop these theories? Isn't the general theory of relativity not right?
So this makes me think, I had to say this. I don't know that Cliff is going to like what I'm going to say, but we were having lunch one day and he told me, he said, very confidential, I had to tell you, Cliff used to be Chandrasekhar's postdoc, only for 1 year, then he got a faculty position.
That's
and
Cliff Wheeler now, right?
Cliff Wheeler, yes.
Yep.
And he told me, I thought that Cliff didn't like, I thought that Chandra didn't like me very much. And I was really surprised because I had the greatest admiration for Cliff. And I asked him why. And he said, well, one day he told me, why are you wasting all this time testing general relativity? We know that the theory is right. So there are many reasons why now that comment by Chandra doesn't ring very right at all. First of all, we know that general relativity is not power counting renormalizable. So people already back in the 70s, starting with work by Stelle and others, showed that if you want to make general relativity quantizable, you need to introduce higher order terms in the action, which are precisely the quadratic and cubic terms I was talking about before. Later on, people developed string theories, and in the low energy theory, in the low energy limit of the theory, what you get are quadratic and cubic corrections of the kind that I was discussing before. So this is the main motivation to look at beyond GR theories from a purely theoretical point of view. GR is not the end-all physical theory of gravity. We know it cannot be quantized. We know that if we want to quantize it, we need to introduce corrections to the action. The second motivation is experimental. We have cosmological observations that tell us that the cosmological constant has a completely unnatural value. And they tell us that there is something called dark energy, of which we know little but the fact that we gave it a name. And there are several people who have tried to explain both dark matter and dark energy with different levels of success, which I will not argue about in terms of modifications to gravity, because the only signatures that we have of dark matter, for example, are gravitational. We have never been able to directly detect dark matter, but we know that by the equivalence principle, it has to interact with gravity in the same way that all other matter does. So.
Thank you, Emanuele. And I liked your connection to Chandrasekhar because he, as a young person, was willing to upend the then status quo and understanding. And now we're expecting maybe the new people that are being educated by these PIRE webinars are going to be the ones who will upend the future of gravitational physics. We're a few minutes, almost 10 minutes past the hour, and I think it's a good time to stop here. Thank you very much, Emanuele. Thank you, everybody, for participating. Please fill the questionnaire, and you will be able to attend again if you want this wonderful webinar on the Black Hole PIRE Science channel on YouTube. Thanks a lot, Emanuele.
Thank you all.